All right, so here we are in 18.2, and in this lesson, we are talking about how scientists study climate change. So we talked a lot about the climate and what it is and what makes it up, but in this lesson, we're going to talk about how scientists even go about studying the climate. Since it's something, remember, climate is over decades, centuries even, so it's hard to study it on a day-to-day basis because it takes so much longer. So we'll start looking backwards. So we have what's called the paleoclimate, which is the climate in the ancient past. And so we need to start there to give us a baseline for how it may have changed since then. So we can study the climate today pretty easily, but we look to the paleoclimate to get information about how it's changed. If we only looked at how it was today, we wouldn't know how it has changed over so many years. So in order to understand paleoclimate, scientists decipher clues from thousands or millions of years ago by taking advantage of the record-keeping capacity of the natural world. So what that means is that we'll talk about this in a few slides, but basically the natural world has done a really great job of storing evidence of what things were like back then. We're not going to talk about fossils today, but fossils are a great example of that. We would never have known about dinosaurs if it weren't for the fossils. So the natural world keeps good record of its past. We also use what are called proxy indicators, which are types of indirect measurement that serve as substitute for direct measurement. So we can't get temperatures from a million years ago because we're not there, pretty obvious. And there was no man to be writing them down. So we use what's called proxy indicators, which are indirect measurement. These are things like ice caps, ice sheets, and glaciers that hold clues to climate history. So one of the biggest proxy indicators are ice cap sheets and glaciers. So scientists drill into them and are able to analyze tiny bubbles of atmosphere, like little air bubbles that were in there that have been there through millions of years. So basically near the poles where it's always cold, so the North Pole and the South Pole, snow is falling, it compresses into ice and can accumulate to be super, super deep. And so what they can do is take ice cores out. So the deeper you go, the longer ago it was formed. And the air bubbles in that ice will have air from ancient atmosphere. So the glaciers in Antarctica have provided information dating back 800,000 years. So that's a long time ago. So since the snow accumulates the ice accumulates season after season, it provides us with a time scale, and we can even look at the atmospheric composition from those times. So from 800,000 years ago, we can know what the composition of the atmosphere was, how many different types of gases there were, which is crazy. So we can also find the greenhouse gas concentrations, the temperature, snowfall, solar activity, and even the frequency of forest fires and volcanic eruptions from any soot that might be in the atmospheric gas in there. Now, we have other proxy measurements. One of them is sediment cores drilled below bodies of water. So basically looking at the soil that is below bodies of water. From that, we can find pollen samples and maybe some other remnants of plants. And that can tell us about the plants that were around at that time, which can help indicate the climate because those two are very closely related. We can also look at tree rings. So the width of each tree ring indicates how much the tree grew in a particular season. So we can use that to study precipitation and drought, as well as fire history, because we may see scorched rings in the tree if there was a fire that season. Then we have what are called pack rat middens, pack rats are rodents. They carry seeds and other plant parts back to their dens, which are called middens, and in caves and rock crevices, and if they're sheltered from rain, and in a very dry area, they can be preserved for centuries. So you can find out more about plant history from centuries ago from the pack rat middens. And coral reefs can give us information because living coral take in trace elements and isotope ratios from ocean water as they grow. And then we can go back and look from hundreds of years ago to see what the isotope ratios were from then. So the amount of data gets smaller and smaller as we go further back, which might make sense. It can either be destroyed or it would be destroyed as the Earth changes. So in Antarctica, we can get data going back 800,000 years ago, but we don't have ice cores around for that long everywhere else. As it gets more north, the amount of time that we could go back would get much smaller. Since we don't have that much data, the estimates of global climate conditions for the recent past are the most reliable. The closer we get to the present, the more reliable they are. This is a graph from the article that's in that lesson, but basically this shows data from the world's longest ice core going back 800,000 years ago. And so what we have here are this red graph is the carbon dioxide in parts per million, the methane in parts per billion. And so we can see that carbon dioxide today is up to 400. And so it was down below 208,000 years ago. The methane is up to more than 1,800 today. Again, around 800,000 years ago. But what we can, and both those two things have increased exponentially in the present. But the thing that we can see here is that there is a definite correlation, a direct relationship between greenhouse gases, these two, carbon dioxide and methane. Remember that methane is much more powerful at heating the atmosphere, but is found much less frequently than carbon dioxide, which is why this is measured in parts per million. So meaning there's out of 1 million gas particles, 400 of them would be carbon dioxide. This is out of 1 billion parts per billion. So out of 1 billion molecules, 1,800 of them are methane, so much fewer. But what we can see is that there's a direct relationship between temperature and greenhouse gases. Everywhere there's a temperature peak, there is a greenhouse gas peak. So the two are definitely related. Okay, so we talked about how we study the past. We study the past through proxy indicators, looking at paleoclimate. In the present, we can use direct measurements. We can literally record the temperature and the rainfall and the greenhouse gases every single day to get current data. So today we have data going back to 1958 when this scientist named Charles Keeling started taking hourly air samples from a monitoring station at Hawaii's Mauna Loa Observatory. So Mauna Loa is a mountain in Hawaii that's the world's most massive mountain. And it is unpolluted, well-mixed air that blows over this mountain, so it's a good place to take samples. So you can see the monthly measurements. Obviously, seasonally, things go up and down, but the trend is upward. So today we use thermometers. We measure rainfall with rain gauges. We measure wind speed with anemometers and air pressure with barometers, and then we can use computer programs to make trends out of it, just like this blue line is right here. And we can also measure the chemistry of the atmosphere and the oceans. But what we can find from this measurement in Hawaii is that carbon dioxide concentrations have increased from 315 parts per million in 1958 to over 400 parts per million today. So that is a direct upward link. So at this point, we have precise and reliable thermometer data for over a century. And also, fishermen have historically kept records of sea ice as well as the length of the growing season. So that's the direct measurement, those three things: temperature, sea ice, and length of growing season. That's the most recent current direct measurements we have. So we talked about the past, we talked about the future, or the present. Now let's talk about the future. The way that we can predict the future is through using models. So we use scientists use a lot of climate models. These are programs that combine what is known about atmospheric circulation, ocean circulation, atmosphere-ocean interactions, and feedback cycles to simulate climate dynamics. So simulate, not stimulate, sorry. And so basically they take this current data, or they enter past data and put it into the model and use it to predict what will happen in the future. And as you could probably guess, these climate models are totally imperfect. They're just a hypothesis because the Earth's climate systems are so complex that many feedback systems are not known. We talked about this, I think, in the climate section, where we can't predict if an input will lead it towards positive feedback or towards negative feedback. We don't know what will happen. We can only make predictions, which is why there are many different climate models that predict either way to see what could happen depending on which way the feedback loop decides to go. And lastly, climate change has already had numerous impacts on the physical properties of our planet, on organisms and ecosystems, and on human well-being. So it has changed and has definitely had a big effect on us. We know that already. It also predicts future changes in these phenomena as well as impacts on wildlife, ecosystems, and society.